So today we'll finally start with derivatives, but before that, just one important concept which I wanted to mention in the when we're talking about metric spaces. This is the notion of completeness. So complete metric spaces. This would be still in the, this should have gone into the preceding lectures about preliminaries. So let's see. A sequence Xn in a metric space is Cauchy if the following holds. Given epsilon greater than 0, there exists capital N such that distance between Xn and Xm epsilon whenever N and M are bigger than this capital. So this definition is formulated, as we know, so that when we can talk about, when we suspect a sequence has to converge to something, but yet we cannot say what the limit is for whatever reason, then this notion of Cauchy captures that situation perfectly, because terms of the sequence are getting closer to each other, and but we are not making any reference to a limit point here. In fact, so what before that? So proposition. If Xn converges to some P, then Xn has Cauchy. In other words, convergent sequences are certainly Cauchy. The interesting thing is the other way around. The metric space is said to be complete if every Cauchy sequence converges. As we know, one example of something which is not complete would be the rational numbers regarded as a metric space. For that matter, even if you take the open interval 0, 1 or any open interval, that would not be complete. So, examples. Our basic example is the Euclidean space. Rn is complete. And in fact, any finite dimensional vector space with a norm is complete. Now, this statement that any finite dimensional vector space with a norm is complete, this requires a little bit of work. If instead of a norm, I had started with an inner product, it's far easier. As we discussed in one of my lectures, tutorials, any finite dimensional vector space with an inner product would be isometric and isomorphic to Rn with the standard Euclidean inner product. Isometric, by isometric I just mean that there is a function from the vector space to Rn which preserves the inner product. And it's quite easy to see that any finite dimensional vector space with an inner product, you can in fact choose that function to be linear as well, linear and preserving inner product. Moment you have that, one can see that whatever happens to Rn, you can transfer it to the vector space. But for a norm, one has to do a little bit more work. Compact metric spaces. By the way, the completeness of Rn is again a consequence of the Heine-Borel theorem. So it's that closed and bounded sets are compact. From that, one can see that any Cauchy sequence will converge. Compact metric spaces are complete. This is a consequence of our definition of compactness. Closed subspaces of complete metric spaces are complete. We can regard closed subsets, not subspaces. Any subset of a metric space is itself a metric space. And if we start with a closed subset and the ambient space is complete, then the subset is complete as well. Right. Now, let's begin the course formally begins at this point actually. So, differentiability. Differentiability. In higher dimensions. So the setup is as follows. F U is an open subset of Rn, and you have a function from U to Rm. As a point in U. So one would like to, what does it mean to say that f is differentiable at U, at x naught? As I mentioned earlier in the tutorial, the key idea is that differentiability should imply that one should be we should be able to approximate the function by a linear function up to first order. What does this mean exactly? So the key point here is that there is one basic difference between the one variable case and the higher dimensional case. if we go back to the case of consider n equals m equals 1. So a real valued function of a real variable, a familiar one variable calculus setting. Here we define the derivative of f at x naught to be minus f of x naught by h. If the limit on the right hand side exists, then that we say f is differentiable at x naught, and we call the value of the limit to be the derivative. Now, obviously one can't make sense of this in higher dimensions. One runs into problems immediately. The problem being that on the right side, the difference quotient I have to divide by h. And when n is bigger than, when the domain is dimension is bigger than 1, rather when the target dimension is when the domain dimension is bigger than 1, then it doesn't make sense to a vector in Rn, and I can't divide by h. So what we do is something which is done all the time in mathematics. If you want to generalize something and the direct definition doesn't work, we sort of recast it in a slightly different way. That's what we can do here. So we recast this as follows. This is equivalent to limit h going to 0 modulus of f of x naught plus h minus f of x naught, this divided by h equal to 0. Well, and how does this help? Simply because I can write this as limit, i.e. h going to 0. I take the absolute value is f of x naught plus h minus f of x naught minus f prime x naught h divided by h equal to 0. Now we have something which can potentially work in higher dimensions, because what I'm dividing by now is norm, absolute value of h, which in higher dimensions I would replace by norm, and similarly the numerator can be replaced by norm in the target space, norm in the domain space. But notice that we have lost something. If we start with this definition, this recast definition, we should already have a candidate for f prime x naught. We should, even before we check this limit is 0, we should guess what f prime x naught is, plug it into this expression, and then check that the limit is 0. Then we would conclude that the derivative is indeed f prime x naught. While in the original definition, even if we didn't know what f prime x naught was, we just had to check that the limit of the difference quotient exists. If it exists, we already get f prime x naught. Well, that turns out to be, I mean, that's something we can't avoid in higher dimensions. So this is the working definition. So let's see. For the general case, for general n and m, we define f to be differentiable at x naught if, now apart from the division by h which was causing problems, I have to also interpret what this means in the general case. See, this expression f prime x naught, this thing here, f prime x naught multiplied by h. Well, f prime x naught can no longer be just a number, simply because, well, f of x naught plus h belong to the target space Rm. Well, h is in the domain vector space Rn. So if this had been just a number, it would continue to be in the domain vector space, and you won't be able to subtract it from f of x naught. So f prime x naught should be something which will take a vector in Rn to a vector in Rm. And so the simplest thing one can think of is, we want f prime x naught to be a linear transformation. So if there is a linear transformation T from Rn to Rm, such that limit h going to 0, norm of f of x naught plus h minus f of x naught minus th by norm h equal to 0. So this is our definition of the differentiability at a point. We t is said to be the derivative of f at x naught and denoted by f prime again it's this line is f prime x naught. This is the notation Rudin uses, but usually people use df at x naught or capital df at x naught. Now, right, I've already, yeah. So what does this say really? It says that if you look at f of x naught plus, if fix the point x naught, look at values of f nearby x naught, in other words f of x naught plus h, where h is small, that whatever it is, it can be approximated by this constant f of x naught plus t of h, which is a linear function of h, linear function of the variable. So it's a constant plus a linear function, and well, up to first order, that means that even after I divide by norm h, the approximation continues to hold, so the limit will indeed be 0. So this part f of x naught plus t of h is supposed to be the linear approximation to f of x naught plus h. Now the second thing is that I said t is potentially it can happen that there are different t's which will satisfy this limit equation. So here I said t is said to be the derivative of f and so on. For this statement to make sense, I need to first check that there's only, if at all such a t exists, t may not exist at all. If such a t exists, it should be unique. So let's check that. So let's call this defining equation denoted by star. Suppose S satisfies star as well. We would like to, so now let's estimate. So, well, let's look at S minus T. No, let's just proceed as follows. So what I have is for given epsilon, there exists delta greater than 0 such that I'm just using the definition of the limit here. The fact that this limit is 0 for t will mean that given epsilon greater than 0, there exists delta 1, let's say. F of x naught plus h minus f of x naught minus th. This divided by norm h is less than epsilon, which I'll write as less than epsilon times norm h. And f of x naught plus h minus f of x naught minus sh less than if norm h is less than delta. Well, actually you'll get two for the same epsilon, one for t, one for h. So I've just taken the smaller, just take minimum of those two deltas. Then you're assured that both these inequalities will hold if norm h less than delta. Now let's estimate, right. Norm SH minus TH. Let's use triangle inequality. SH minus f of x naught plus h minus x naught plus so I just added and subtracted this f of x naught plus h minus f of x naught here in the here, and then I write it like this. So this will be, both of these are small. So if this is 2 times epsilon times epsilon norm h. Well, now what I can do is, so ultimately I'll end up getting SH minus TH. So if norm h is less than delta, is less than or equal to 2 times epsilon h. If norm h is less than delta. Well, I can just, at this point, I can just take x, any arbitrary x in Rn, then I multiply it by a scalar if modulus t is small enough. Actually, modulus t, I'm going to multiply t with x and put that as h. So that should be less than delta. Small enough here just means that modulus of t less than delta by norm x. Then I just want to ensure that this is less than delta. Then S Tx minus T Tx, this thing will be less than epsilon Ex. So I can bring the t out. The t comes out with an absolute value sign on both sides, which implies norm Sx minus Tx less than epsilon times norm x. Now here, and this holds for all epsilon. Whatever epsilon I have given, I can take t sufficiently small and I'll end up with, so I can fix x and vary that small t and I'll end up with this. So since this holds for all epsilon, which this implies that this holds for all epsilon greater than 0 for a given x. Therefore, you immediately conclude that Tx equal to Sx. So this proves that this T is, if at all it exists, it's unique. So let me stop here and continue with the chain rule next time.